Hello students. So in this second lecture we will be seeing second lecture of deflection of beams using energy methods. So first lecture we have seen about strain energy. Okay. Now here in this particular lecture we are going to discuss about four topics. That is virtual work, then Bernoulli's principle of virtual displacement, principle of virtual work for deformable bodies, and unit load method. So first 3 points we are going to see in a it's a small content, but unit load method will be seeing in detail. Now strain energy method, it was seen that with whatever research happened, it was seen that strain energy or real work method, it is having limited use when we have to calculate displacement. But this virtual work method, it is very powerful. It was found that this is most versatile and powerful method. So here, before we move to the point number second, what is Bernoulli's principle and what is principle of virtual work, first we will be seeing about what is virtual work. So starting with virtual work. So here, let us consider one body. Let us consider one body and some loads are acting on it. So let us draw a body subjected to real loads and will show a virtual displacement. So suppose this is some body, any body we can consider, and some loads acting on it. So P1, P2, P3, P4. Okay, so because of this load there will be some displacement. So let us consider it is simply supported. So there will be some deformation in the body. Okay, so let us draw some deformation. So we can call it as hypothetical deformed shape. So this is particular body which is subjected to real forces P1, P2, P3, P4. There can be n number of forces. So because of these forces the body will undergo some deformation. Okay. So here this hypothetical deformation is called as actually virtual deformation. This is a virtual deformation, and the work done by real forces due to this virtual displacement is called virtual work. Okay. So this hypothetical deformation is nothing but it is hypothetical deformation. It is nothing but this is virtual deformation. Okay, it is nothing but virtual deformation, and the work done by real forces due to this virtual displacement is called virtual work. Okay, so that is the simple point we want to convey here. So virtual means actually its effect exists. Okay, its effect exists, but it actually it's not in fact, but effect is there. So virtual work can be defined as the work done by real forces due to hypothetical displacements, or the work done by hypothetical forces during real displacement. Okay, so work done by real forces due to hypothetical displacements, or the work done by hypothetical forces during real displacement. So that is work done. So coming to our second point, our second topic is what is the Bernoulli's principle of virtual displacement. So this is our second case, Bernoulli's principle of virtual displacement. So here also similarly we are going to consider the body what we have considered just now, and some loads. Okay, P system of forces, and also moment is acting. Okay, so we are going to consider the px and py component of force, that is in x and y directions, and then we will be considering some equations, that summation of forces in x direction and y direction, and overall summation of all the forces, finally it should become equal to 0. So let's see this. So each load will have some components. Okay, each load will have some x components and y components. So we are going to use three equations, important equation. Summation of forces in x direction is 0, summation of forces in y direction is 0, and yes, this particular body is also carrying some moment. Okay, so let us call it as moment 1, and then let us call it as moment 2. Okay, so initially this is the body. So suppose so final equation we will also include these moments. So summation of forces, these moments, then px into y plus summation of forces py into x, okay, is equal to 0. So forces in x direction is 0, y direction is 0, and moments equals to 0. Okay, so this is our body. Now suppose there is some virtual displacement we are giving o dash. Suppose this is the origin. So if we want to give some displacement o dash, okay, some displacements if we want to give in this direction, so then the component of o dash in x direction be delta x, and in y direction be delta y. So and it is a rigid body, so all forces will have displacement delta x and del y in x and y direction. Okay, so when we give this displacement, so components of all forces, okay, components of this o dash in x direction if we consider delta x, and in y direction as delta y, so all forces, okay, all forces will have its displacement in delta x and delta y, that is in x and y direction. So finally we can write virtual work done is equal to, we can write virtual work done is equal to summation of forces px del x plus summation of forces py del y. Finally this equation, okay, this should equal to 0, and we also have summation of forces px and py is equal to 0. So overall, you know, virtual work done is equal to, virtual work done is equal to, it becomes 0. Now let us consider the rotation of rigid body by a vertical virtual rotation d theta. Now for this particular body, suppose it is rotating by some angle theta. So if a point q yx qxy, okay, so suppose we consider any point qxy, and it is at a distance of r from the origin, then let us draw this figure. Suppose we consider any point, suppose for this particular body, okay, if we are considering any point, we are considering any point, and we are considering a small rotation, virtual rotation d theta. So if a point qxy is at a distance r from the origin, so if we consider any point here, and it is at a distance r from the origin, okay, so this is the point, let us call it. This is x-axis, this is y-axis, this is our angle theta, this is our origin. So for this particular point, if we consider this, then this will be r d theta, okay, and this angle will be theta, and this length will be small del x. Okay, so we can write it as del x is equal to r d theta sine theta, then which can also be written as y d theta, and for del y component we can write it as r d theta cos theta, which is also equal to x d theta. Okay, so finally virtual work done by real forces due to virtual displacement, so that we can calculate, we can write that equation as summation of moments of d theta plus summation of all forces in x direction del x plus summation of forces py into del y is equal to, this is virtual work done. So this is Bernoulli's principle, virtual work done by real forces. Okay, so here when we summation of a moment d theta, summation of forces px, now this del x is nothing but y d theta, and del y is nothing but x d theta. So when we substitute these values, summation of y d theta plus summation of py x d theta, So we can take out d theta as common factor, and we can write summation of moments plus summation of px into y and plus summation of py into x. So finally, with our previous equation, all the summation, summation of this all, this was equal to 0. Okay, so our finally virtual work becomes, virtual work is equal to 0. So from all these equations we have written, so we can conclude that if a rigid body is in equilibrium under a system of forces and or moments, the virtual work done by the system of forces or moments during virtual displacement is 0. Okay, so if a rigid body is in equilibrium under a system of forces, if a rigid body is in equilibrium under system of forces, under system of forces, the virtual work done, the virtual work done by this system of forces, by this system of forces and or moments during virtual displacement is 0. So this was Bernoulli's principle. Okay, now let us move to the third case, principle of virtual work for deformable bodies. So here also let us consider an elastic body, and then let us draw the similar diagram. Here a body which is, or we can simply refer to this page. Okay, so if we consider similar body, okay, a body, uh, now let us consider an elastic body. Okay, let us consider it as an elastic body, so which is subjected to system of forces. Okay, so these forces can cause real internal stresses, and every element in the body is in equilibrium. Okay, every element in the body is in equilibrium for this particular case. Okay, so there are, what did I say, this is the number one point, this is elastic body. Okay, which is subjected to system of forces, and these forces can cause internal stresses, and every element in the body is in equilibrium under the action of external forces and internal forces. Mean there are some external forces, because of that there are some internal stresses occurring, but body is in equilibrium. Okay, so that is the important point to remember. Now, uh, if we imagine, okay, if we imagine that some virtual displacement is given for this particular body, suppose we give some virtual displacement, that means we are giving some, because this displacement is because of some hypothetical force system. So if we say that some virtual work because of these external forces, okay, it will happen, virtual work because of this displacement it will happen, and this body is in elastic, so there will be some virtual displacement and also virtual deformation. Okay, so two things will happen, virtual displacement will happen and virtual deformation will also happen. Hence the external work applied to the element, it will be in two forms. So there will be virtual work, and then there will be second virtual work of deformation. Okay, so here what we can write, as a principle, let's write it as a principle, that if a deformable body is in equilibrium, if a deformable body is in equilibrium, under a system of forces, under system of forces is given virtual deformation, then the virtual work done by the system of forces, then the virtual work done, then the virtual work done virtual work done by the system of forces is equal to the internal virtual work done, is equal to the internal virtual work done internal virtual work done by the stresses due to that system of forces, by the stresses due to that system of forces. So if a deformable body is in equilibrium under a system of forces is given virtual deformation, okay, when it is given a virtual deformation, then the virtual work done by the system of forces is equal to the internal virtual work done by the stresses due to that of system of forces. Okay, so this above principle, it is free from the system causing deformation, and hence it can be applied to all cases of deformation, that due to loads, temperature, settlement of support, lack of weight, etc. Okay, and this equation is valid for all elastic material. So this is our third point. Now let us move towards our next derivation for unit load method. Okay, so let us see unit load method, the fourth point. Okay, so unit load method. Now here also we are going to use the same diagram, unit load method. Okay, now here let us consider this body, where quickly let us quickly draw a body. Okay, and this body is some external forces acting on this P1, P2, P3, P4. So some n number of forces acting. Okay. Now again it is, let us show it as a simply supported. So these all external forces, they are applied gradually. So let us see the displacement under the load at points B, delta 1, delta 2, delta 3, delta 4. So wherever this force is acting, there will be some displacement. Okay, so at this particular point of action of load, okay, so wherever this load is acting, let us consider that for this corresponding to this particular load P1, let us see that there is displacement delta 1, here it is delta 2, here it is delta 3, here it is delta 4, and this is delta n. So wherever load is acting, there will be some displacement. So with this we can simply write the external work done. Okay, we can write that external work done is external work done is equal to half of delta 1 P1 plus, we can write for all the forces, half of delta 2 P2 plus half of delta 3 P3. Like this we can write for n number. Okay, 1 by 2 delta 3, sorry, delta n Pn. And strain energy stored, and strain energy stored will be our equation, half of P into E, half of P into E dV, half of P into E dV. Okay, so where P is stress in this case, where P is stress and E will be strain. So in this particular case, this is stress and this is strain. Okay, now we can simply compare these two equations. So this is equation number 1 and this is equation number 2. Okay, we can simply write this equation. So this external work done is equal to strain energy stored. So when we write this is equal to this. So now let us consider the same body. Okay, I'm just writing that equation number equal 1 equal to 2. We can write this equation. Okay, now let us consider the same body. It is subjected to an unit load applied gradually at C. Okay, let us consider any point C where it is free of system of forces P. Okay, so whatever P number of forces we have given. Now let us consider that this same body. So same body. I'm just drawing. Please assume it as the same body. Okay. So this same body, it is subjected to an unit load. Okay, gradually at point C. So let us consider any point C here. So for this particular point C, where unit load 1 kilonewton is acting, okay, and it is free of system of forces. Now there are no external forces. So let the displacement at 1, 2, 3 and be delta 1, delta 2, delta 3, delta n. So whatever points initially load was acting. So at those points, let us consider only unit load are acting now. But let us consider that there is some displacement. So delta 1, delta 2, delta 3, okay, wherever previous loads were there, delta 4 and some similarly delta n. Now we are considering these are the displacements. Let the displacement 1, 2, 3. So delta 1, delta 2, delta 3 we consider, and displacement at CB delta. Now let the stress produced. So if we consider any element, any small element here, okay, if we consider any small element here, so here stress produced, okay, any small element. So stress produced will be P dash. Let us consider that stress produced is P dash. Stress is equal to P dash and strain is equal to E dash. Strain is equal to E dash. Then in this case, okay, then in this case external work done, okay, this is now when we are considering it as unit load. So external work done, we can write it as half of 1 into delta, okay, because unit load is there and the corresponding displacement is delta we have considered. Okay, so internal, this is external work done. Now what is the internal work done? So internal work done will be, so we are using the similar formulas, okay, only we are replacing this delta with this delta and P with unit load. Okay, now the same internal equation, same equation, P dash E dash dV. Okay, now when we again compare these two equation number 3 and 4, if we write it, okay, so half of means external work done equals to internal work done, half of P dash E dash dV. So when we write like this, now if P system of forces is applied to the body, then external work done as we have got here. Okay, so with this, now for this particular body, let us apply all this P system of forces. Okay, I hope it is clear. First we have just considered the system of forces with this P1, P2, P3 loads. Okay, this is, for that we have got this set of equations. Then we have considered only unit load and we have got this set of equations. Now if this P system of forces, okay, they are applied to this second, okay, means now first system, if in addition to this unit load, if this second set of equations, okay, if we apply it here, then our these equations, what will be the change? So our external work done, this equation will be, we will simply add this particular factor over here. Okay, so our equation will change as, so let me write it here. So if P system of forces is applied, P system of forces applied there, then external work done will become, external work done will become half of del 1 P1 plus half of del 2 P2 plus half of del n Pn plus, because of unit load, 1 into delta. Okay, now because unit load is already acting, so internal work done internal work done will be integration of half of P into E dV plus PE dV. Okay, since the stress P dash is acting throughout the deformation, now equating internal work to external work. Okay, now P dash is acting. What was P dash? P dash was when we have considered this body. Okay, a small element we have considered, and this was the P dash was the stress here. Okay, so since this since the stress P dash is acting throughout the deformation, so when we equate internal work to external work, so when we equate internal work to external work, to external work, so we get half of delta 1 P1 plus half of delta 2 P2 plus, we will write this all equation. Okay, plus 1 into delta is equal to, so we are simply equating these equations. Okay, half of PE dV plus integration of PE P dash E dV. Okay, so initial our first equation. Okay, so if we consider here, okay, so this was our equation, half of del 1 P1 plus half of del 2 P2. So this was our previous equation, equation number 1. Okay, so in this equation, so when we subtract equation this number 1 from our latest equation. Okay, so our latest equation, this equation. Okay, this is our latest equation. So the previous equation, when we subtract with this equation, so we arrive at 1 into delta is equal to integration of P dash E into dV. So we can write delta is equal to integration of P dash E into dV. So where delta is the deflection at point where unit load is applied. Okay, this is the deflection at point where unit load is applied. Okay, unit load is applied, so that is that point. And P dash is stress in an element due to unit load. Okay, this is the stress in an element due to unit load. And E dash is strain in the element due to given load system. Okay, so this is unit load method. So we are going to use such equation to solve the problems. So hope this lecture is clear to you. Thanks for watching. Thank you.